Hello and welcome to the Smartest Dummies podcast, very first edition. My name's Carson,
And I'm Elijah.
and today we talk about some cool stuff about the Higgs Boson and some cool stuff about the Standard Model.
Yeah, this is our first podcast, so we're really excited to do this. Like I said, it's the first one, so go easy on us. We're going to give you our social media accounts, and
We
we'll
want some
appreciate any
review.
feedback that you can give us.
This is going to be a podcast just about anything we want to talk about, really, but we're pretty much science focused. We'll be like physics, with a bunch of other cool things like that. We're really interested in a lot of wonders of the universe, just about anything, but we're also open to other ideas, just people and fun topics and social stuff, and just chill conversations. Basically, just two dummies trying to get smarter.
Yeah, we
That's
enjoy
the
learning,
info.
so that's what we're going to do. We're going to learn and have y'all learn with us.
Cool. Alright, so we're going to be talking about a little bit of the history of elementary particles. It started off with just elementary, I guess the word for like elements type, yeah.
And there were 4 of them.
There was 4. It was it started off with fire, water, earth, and air. And then obviously later on, through the studies of particles and particle physics and things like that, we came across pure elements, atoms. And then
Pure elements and then atoms.
yeah, so
Atoms are what make up the elements.
yeah, it was like solid gold would be a pure element, and then what makes up the individual things of that would be atoms. And then later on, even further, we discovered those were made of smaller things like electrons, protons, and neutrons. And then as we progressed through that, they had to come up with a lot of different things for it, and the evidence that proved those, and like the new theories describing them, created more evidence for things that are even smaller than that, which led us into
Modern day, physics.
like the Standard Model, and leading into all the research that's going on at the
Yeah.
Large Hadron Collider.
So back then, we kind of hit a standstill. We knew that they were atoms and that they're made of protons, neutrons, and electrons. The protons and neutrons making up the nucleus, and the electrons kind of orbiting the nucleus, you could say.
In orbitals.
In orbitals. Yeah, but like I said, we hit a standstill, and it wasn't until we started building particle colliders that we were able to find out what those protons and neutrons are made of.
Mm-hmm.
So there were a lot of particle colliders built, but the one we're going to focus on today is the Large Hadron Collider, which is by far the most powerful of the ones that we have.
And it's the largest.
Yeah, it is also the largest machine ever built by mankind.
There's over 10,000 scientists from like 100 different countries, something like that.
Yeah, and it's been a big international.
Yeah, it's a very uniting
collaboration.
thing of scientists.
Basically, the rundown of the Large Hadron Collider, it smashes protons together, and we don't want to get too complex into how it does it. All you have to know is that it shoots them around this huge
tiny
loop
tube.
in this tiny tube going very, very close to the speed of light, like 0.9999 the speed of light.
Yeah, and basically they just push them with these extremely large magnets, and then they have these 4 main observatories where they actually monitor the
collisions themselves.
Yeah, the collisions themselves, and they can remap where they were inside the protons. And they also are there's so many of the sensors that they need, because some could just go through all the walls.
Yeah, they're going so fast. They're such a high energy that they could just.
You could even like he was telling me, the large concrete wall or whatever for protection.
Yeah, actually the beams are so powerful, the beams of protons themselves that are going around, that they can't just stop the magnets from working, because those are the things that like hold it in the tube, right? Because if they did that, then the beams would just go off all over the place wherever they wanted, and they'd mess up the machinery. So what they have to do is they have to have this particle dump. It's this huge block, 2-ton block of graphite, surrounded by a couple tons of steel, that's surrounded by a couple tons of concrete, where they just shoot all the particles every 10 hours when they get too high of an energy. And yeah, that thing, basically, the particles are such a high energy that they could melt up to, I think it's like 2 tons of copper. So yeah, they're really hot.
There's just so much energy in them. Alright, so an important factor that needs to be well understood before we can go into some other topics we want to talk about. Things like light and things with super high energy, like for instance, light, a single photon technically has no mass, and it can't really be a particle, but it's also a wave in a way. It has a wavelength of light, and we know that because different colors. It's on the spectrum.
Yeah.
And because it has such high energy, it gives it mass because E equals mc squared, and it's kind of like it can't have zero mass. It has so much energy.
E equals mc squared is an equation Einstein came up with. It has to do with relativity and stuff that we won't get into at all. But basically, all you have to know, E stands for energy, and then you have the equal sign, and then you have m, which is for mass, and then c squared, which is the speed of light.
Mm-hmm.
And basically, all that's saying is that if you have enough energy in any given system at any given place, then mass can be created from that energy.
Mm-hmm.
And you may have heard of like the fact that energy can't be created or destroyed, right? That's what thermodynamics. And it doesn't violate that because that mass comes from the energy. The energy is
being distributed.
Right, it's being distributed. Mm-hmm. And it just, you could think of mass as energy or energy as mass. You can go back and forth.
Yeah.
So yeah.
A major factor that goes into this as well is in the timeline of like the arrow of time that we see it as in, disorder likes to go like greatens, as in like when a glass falls off a table, it shatters. It doesn't come together and land back on the table. So as disorder increases, that's the same way as entropy. So this is a good example of how energy isn't being destroyed. It's just being distributed. Yeah, this is called entropy, which is another fundamental thing
for thermodynamics. Yeah. So one last thing we need to cover before we can get into the Higgs field. It's
fields in general.
Quantum field theory is what it's called. So like, we just talked about E equals mc squared, right? Well, now we need to talk about how every particle there is, theoretically, can have a field. So that means electrons can have an electron field, photons can have a photon field, protons can have a proton field, and so on.
And there's theoretical fields that unite gravity and things like that with like theoretical gravitons. That's a whole other theory. We haven't observed that yet.
Yeah, that's still theoretical. Observed. And these fields, they exist all throughout the universe. If you have enough energy in that field, then the field will start to vibrate. The particle will arise. So
this goes
that
to the
whole
uncertainty.
Theory, right? And that whole theory is what basically allowed us to discover the Higgs Boson particle. So the Higgs Boson particle, it doesn't exist on its own.
It's more of a it's more of an action.
Its natural state is a field.
Mm-hmm.
So like, in order to prove the existence of this field, we had to pour enormous amounts of energy
and a lot of data. That's
we
why
had
it
to
took
take
so
a lot
much
of
time
data
to be able to find and even observe it.
Mm-hmm. And these protons that were colliding at the LHC, the Large Hadron Collider, they were so energized that they allowed us to detect the Higgs boson in a way. In reality, the Higgs boson is so small, though, that we can't actually see it. So what we detected is the
reaction of it.
Yeah,
the decay.
It's
effects on the other particles.
On the other particles, right? On the environment. Right.
And another interesting thing that goes into this as well is like the Heisenberg uncertainty principle, and it's like quote unquote true randomness. Obviously, a lot of things were random, like quote unquote random, until we figured out. So right now, like things that decay, like such as like muons from the sky that constantly there's like 10,000 of them per cubic meter. Right now, like in this
space
very
particles, you could think of, they're just shooting through space.
Yeah, they're shooting through our atmosphere, like this decay in general of particles, and they're the only truly thing that we can currently observe as a random.
Yeah.
And we're getting to the point where we don't want to say that we've gotten to the point where we can. There's the smallest thing, like the smallest unit, but it's like we're getting there to where we're almost getting optimistic to where we're about to find it. And it's more at this point just things are just behaving so strangely that there's so many countless things to take into measure, and it's difficult to even have any set laws.
And that reason right there is why it's so important to understand the fundamental fields that govern the universe. Because if you can understand those, and you can build upon that and build upon that, and eventually be able to predict complicated phenomena of
like some extreme forces,
fluid dynamics, or something like that.
Like true chaos, like randomness. Well, eventually, in a theoretical sense, there could be one unified theory. However, more likely is that we're only ever going to get infinitely closer and closer, and probably have a couple theories that work for majority of cases. But there's always going to be little things that we're going to have to kind of work around.
For example, like on a side note, Newton had his law of gravitation, right? Well, it didn't work for one planet. The prediction was a little off, and so then Einstein came around with his general theory of relativity, and he was able to predict the correct orbit of that given planet. And so that's just an example of how, you can start to go deeper and deeper into the fundamentals of something in order to predict more accurately later on.
And then Einstein, even in his final years of study before he died, he majority of his time and efforts were spent failful attempt, sadly, that he was trying to discover a unified theory. And he was a bit stubborn with relativity. He wasn't one to appreciate quantum mechanics as we do today, even though his work was one of the main leading sources for people to discover a lot of fundamental rules and laws in quantum mechanics. And later down the line, a lot of the things that we've discovered about quantum mechanics and smaller fermion particles and how they behave and how they decay has led to our theory of a better understanding of the universe and several theoretical theories, which is like a whole other deeper thing. Like theories that could be a thing for a unified theory. There's so many theories. But another subject is we can never have a true proven unified theory, because theories are just that, theories. They can never be proven.
Mm-hmm. Basically, you're setting it up to fail. Mm-hmm. And you just have to fail over and over again. And so that's just the nature of a theory.
Yeah. And even a lot of laws, they behave weird in certain circumstances. For example, another cool thing is, for the longest time, people thought the Earth was flat, and that you could fall off the edge.
People still think the Earth is flat.
Some people. I swear those people are hilarious. Oh my gosh. No, but that's a great example. And then eventually people are like, oh wait, I can sail directly around the world. That's a cool thing.
Oh wait, the mast comes up over the horizon before the rest of the ship does.
Oh yeah, and our sun, it has a lot of things sort of going on there. That's strange. It looks like its mass is so large that there's no way it could be that close to us. I suppose maybe we're orbiting around it.
Right.
With how much energy it's putting out. No, it's cool because, that's just how things evolve. And maybe eventually a lot of things that we understand right now could be, looked upon even 50 years from now. I'm like, haha, that's so funny they actually believe that. Mm-hmm. What a waste of time. But that's just the cool stuff with science. It's just deepening your understanding of the universe, because we're lucky enough to have a universe where people were able to develop in a way that we can even ask questions like this.
Yeah, one of the strangest facts of the universe is that it can be predictable.
Yeah.
In some aspects.
And the entire thing of predictability is just, it goes back into the sense of order and disorder and entropy of the universe. And I just finished Hawking's A Brief History of Time, and towards the end he discussed a couple things, but one of the major things was that in our universe is expanding, as we all are well documented and that we know, and there is a possibility, but it's very unlikely because it's at that critical speed where it couldn't start recollapsing. But if it did, it was theorized that in the recollapse, it could be theoretically possible that things would almost seemingly go backwards in order, which they would go from a disordered state to back into the ordered state. Later, this was disproven, and it has been proven that it would continue to disordered
until the very final moment.
However, humans will not be able to be alive to observe or measure any of this during this moment of recollapse. So that won't happen. You'll be spaghettified.
Yeah. So back to the Higgs field. So, like I said, there's a bunch of fields for every given particle, but the Higgs field is, you could call it more fundamental than all the others, and it's more important too. So, what the Higgs field does is it gives elementary particles mass. there's two categories of elementary particles in the standard model. There's fermions, which are all the particles that make up matter, which are quarks, which make up protons, and then there's also like electrons and stuff. And then there's bosons, which are force carriers. We won't talk about them much. All you have to know is that they exist, and that the Higgs boson is a force carrier. So those quarks and electrons and all those other elementary particles, they have masses, and they're different masses. They're not the same. And
that's one of the main things that how we identify the difference between them.
Right.
Because at this small of a scale,
there's not much you can observe.
There's not much that you can observe that's different. Yeah, that's interesting. It's more of just things aren't just like the way they are. It's more of just the way they behave. It's just like you can't say like for example, this is a very rudimentary like basic way of saying it. Like you could say the difference between up quark and a down quark is the same as a giraffe and a rhino. Like they're made of the same particles in a way, like carbon and like oxygen and
like
water.
They're all made of protons.
But they're like they just behave differently in a way that builds this giant thing. It's like how DNA is all made of the same stuff, but just different alignments, different combinations make up different things. And quarks themselves are just different sizes and different like energy levels. And there's another great part to this. Every single like smallest thing that we could find, there is, for a fact, as we know, there must be an anti-variation of all of them. So that's a whole nother tangent that we just could not. A lot of scientists we just don't understand yet, because there should be a lot more observable antimatter in the universe. However, you can't really, because the second, like, we've created some, I think a couple like anti-electrons or protons, but the instant they come into existence, they collide with another
proton.
And then they instantly a slight little burst of light that they turn into, and they're gone.
And they annihilate each other.
Mm-hmm.
But so the reason these different particles, elementary particles, have different masses is the Higgs field. So the Higgs field is kind of this this predictable phenomena that we just had to find, because we knew that something had to give these particles different masses, and it sure wasn't gravity. Gravity's too weak. So they invented this theory, which was the Higgs field. And so you can think of it like this. Any given particle, it's going to have some type of mass that's designated by the Higgs field. And so, like, if you think of an electron flying around an atom and it's hitting other electrons, right? Well, that that's a bad analogy. What's that one analogy?
Alright, so into the Higgs field, the analogy at CERN, that one, a bottle of champagne, it was a TED Talk that was the best, but for copyright reasons, we will not be playing that. But
we're going to give our best.
Yeah, basically the analogy.
The TED Talk in our own words.
Yeah, the analogy went like this, okay? So, imagine the Higgs field is a group of people at a party.
A group of
like they're all uniformly spread.
Right. The important thing to note is that these people are physicists that were at the Large Hadron Collider when the Higgs boson was discovered.
And then imagine that Peter Higgs himself began to the room, because on the other side of the room there was a bar that he wanted to go.
Trying to cross the room, basically.
He wanted to go get a drink, right? But obviously all the physicists would want to talk to him. So they would meet in the middle, and he would be slowed down getting to the bar. This is what is giving Peter Higgs mass.
You could think of Peter Higgs as a particle with no mass before it enters the room.
And imagine another man that was a tax collector that no one liked. He could go straight through without talking to anybody.
He could cross the room.
Outside of the room, outside of the room, these two are equal, right? Like, they're the same, like, fundamentally. However, in the room, the Higgs field is what is giving the particles mass. Right,
the Higgs field being the crowd.
Mm-hmm. Which is basically like this uniformly spread thing across the universe, which is just like... Everywhere. And imagine clumps, like it clumps together, and it is the mass behind things.
Right, and all waves can become particles when enough energy is dumped into it.
Mm-hmm.
the Higgs boson particle, you could think of it as a rumor that started at one end of the room and traveled to the other side. People are going to clump up to talk about it, right? And as the rumor spreads around the room, that clump will spread. You could think of that clump as the particle of the Higgs boson field, or the Higgs field.
And yeah, basically there's no person there. It's just a clump in the field.
Right.
And that's the Higgs boson. That's the Higgs boson particle. And that's the difference between the Higgs field and the Higgs boson particle, which is they're the same thing.
It's just
different actions.
Phenomena of the field.
Yeah, it's just a phenomena. It's kind of like, imagine you're in like a pond, and then there's a slight ripple in the water.
So, a quick recap. Elementary particles. So, the biggest thing to take away is that all these particles have different masses because of the Higgs field, and these different masses lead to different properties of those particles, which allows for protons, neutrons, and all those other particles to exist. It's important to note that protons themselves, which are not elementary particles, they do not get their mass from the Higgs field. So let me list off the fundamental particles so that you know which ones, so that we're all clear. So there's quarks, which make up protons, and then there's leptons, which you can think of as electrons, and then there's force carriers, which don't have mass at all, so it doesn't matter. But anything other than that, they do not get their mass from the Higgs field. So the quarks make up about 1% of the mass of a proton. There's 3 of them total inside the proton, and they only make up 1%. The other 99% comes from Einstein's equation E equals mc squared. Basically, it's energy. And that energy is coming from the quarks and this other particle called the gluons interacting. So the quarks themselves, they wouldn't be bound together to make a proton without the gluon field. Gluons themselves are massless. You could just think of them as glue, which is pretty easy to remember, I think. So the interaction between the gluons and the quarks is so powerful that it gives the proton 99% of its mass.
Yeah,
which is really pretty amazing.
In the A Brief History of Time, he did an analogy. It was at that level of smallness, if each particle was the same as a rubber band, an electron or whatever would be like being held in, the rubber band would have the pull force of a ton, and then on the inside of like the quarks and stuff, it'd be like 100 million tons.
Yeah, the gluons are very, very strong. So strong, in fact, that they give rise to what's called the strong force, one of the 4 fundamental forces, which is what holds protons together. So it's so strong that it can hold protons together while it's holding quarks together, which is a whole nother subject to talk about. Yeah,
the force can't really. It's been like measured, but it's like you can't. The same energy. This goes back as another fun thing with quarks. The same energy that it takes, because they come in pairs, and like a lot of times you'll find that with there's not just 3 quarks that make up a proton. A lot of times, like you'll find that it needs those 3.
Right,
but they
there's other pairs that come in and out of existence because of the massive amount of energy.
Yeah, the quarks. This is why we think that we're getting optimistic that we're finding the smallest thing, because the quarks take so much energy to pull apart that by the time you put that much energy to it, a whole new quark has been made from the energy that you put into it.
Yeah, and it just pops up right in between them.
Right in between them. It's just like, you're like, okay, where do I go now?
Yeah, because, again, E equals mc squared, you have enough energy, you're going to get mass.
And this was how the beginning of the Higgs was theorized, because it was like, alright, so we can't find smaller particles, but we can find is the things behind them, which is like fields and energies, which is where we are now, and that's why we're on the search for a theory that can unify them, and which makes it extremely difficult, but it's a
challenge. Ready
it's an optimistic challenge right now.
Yeah, and you may have heard the Higgs boson be called the God particle. I
love this name for it.
Not many physicists are very fond of that name. The reason they call it that is because it's such a fundamental field, because it's what allows those different diversities of fundamental particles.
Yeah, and it's really interesting as well, because back in the day, like during Einstein and Newton and all of them, a lot of the, like, what would be officialized as a new agreement of science to move on and, like, consider this theory not a law, because it's still a theory, but plausible, it would have to go through churches and things like this. And so it's important to take into account the possibility of an overall, beginning. And this kind of goes back into prediction. If you have an overall perfect understanding of any single point of the universe, then you can predict the rest, past and future. And that's why a lot of people are obsessive over discovering the beginning, because this goes into with the church and what theories they would allow to get passed. I want to say it was Galileo, whenever he first proposed that I think it was the Capicaro, something like that, that all the bodies in our solar system went around the sun. The church was not fond of this, and he got sentenced to life. What's it called? House arrest. And a lot of his works were have to be published and smuggled from his house. And once these were published, and everyone was like, "This guy's the smartest person. Y'all wilding over here." And so they were like, "Okay, yeah, we accept this. This makes a lot more sense." And then they started getting out the Earth isn't flat, and it just moves on to it. And it's an interesting point that it's called the God particle, and it sort of unifies full circle.
Yeah, well, not full circle because
we're still
the data for the Higgs boson is actually not 100%.
But
they've only done it 1 or 2 times.
It's widely accepted, and I think it's a good way to think about things.
Yeah, and I guess that's where we're going to end it today. Hope you enjoyed it.
We're looking forward to a lot more of these, hopefully.
Yeah.
To the conclusion. All right, so social medias. We made a couple for this. It's the Smartest Dummies podcast on Instagram, and then on Twitter it's just Smartest Dummies. This is our very first edition, so
give us some feedback.
We would appreciate a lot of feedback. Obviously, this episode might be a little bit shorter. We're still new to this, but we're looking forward to a lot more episodes. We got plenty of ideas.
Yeah, we enjoy learning, so we're all about it.
We're all about it, and we're open to all sorts of other cool things too. We don't need to just talk about
physics or
science. We're open to a lot of different things. We're just sort of having fun with it.
Yeah, hope you enjoyed it. See you guys next time.